In today's lecture, we will be discussing partial orders and partially ordered sets. Let us consider a set A and a relation R defined on the set. We have already seen that if R is a relation on A, then R is a subset of A cross A, or in other words, a relation on A is a subset of A cross A, which we write in symbol as R subset of A cross A. We have also discussed that there are special properties of relations, and we will recall three properties that we have discussed before. The first one is reflexivities. A relation R on A is said to be reflexive. R is said to be reflexive if A related to A for all A belonging to capital A. Next property that we recall is antisymmetry. A relation R on A is said to be antisymmetric if A R B, that is A related to B and B related to A together implies A equal to B. So, R is antisymmetric if A R B and B R A implies A equal to B. Finally, the third one that we need in today's lecture is called transitivity. R is said to be transitive if A related to B and B related to C implies A related to C. Now, a relation R is said to be a partial order if it is reflexive, antisymmetric and transitive. A relation R on a set A is said to be a partial order if it is 1 reflexive, 2 symmetric, and 3 transitive. This is a special class of relations that we study extensively, and therefore, we have a special symbol to denote partial orders, and the symbol is well known less than or equal to. So, usually we will denote a partial order by this less than or equal to symbol, but we have to keep in mind that it is something different than the usual less than or equal to that we use in the context of real numbers or integers and so on. So, if I have a set A on which a partial order denoted by this less than or equal to symbol is defined, then we will write this whole system as A less than or equal to, then all braced by a third bracket, and in between we put a semicolon. So, when I say this, I can say that this is a partially ordered set. So, if I say that I am considering A semicolon less than or equal to symbol, then this means that A is a partially ordered set with respect to the partial order denoted by the less than or equal to symbol. All right. Now, of course, this less than or equal to, although it is not really the less than or equal to that we are familiar with, raises a question that what about our usual less than or equal to? Is it a partial order? The answer is yes. So, the first example of partial order that we will discuss in this lecture will be on the set of integers which we denote by this special symbol capital Z, and the partial order will be denoted by less than or equal to, and this is indeed the less than or equal to in the sense of the ordering in the set of integers, that is A is less than or equal to B if and only if B minus A is greater than or equal to 0 in the usual sense. So, I will write in the bracket in the usual sense. Now, we can quickly check that this is indeed a partial order, because if we take any element A inside the set of integers, we do not have to explain much to tell that A is less than or equal to A for all A belonging to Z. And then if we take 2 integers, and suppose these two integers denoted by a and b are such that a is less than or equal to b, as I have already written, and b is less than or equal to a, then together they will imply a equal to b. So, we have antisymmetry over here. Finally, again it is pretty much obvious that if we have a less than or equal to b and b less than or equal to c, where all of them are integers, then I can write a less than or equal to c, which is transitivity. Therefore, we see that the set of integers with the usual less than or equal to relation is a partial order. At this point, I would like to mention that this set Z along with the less than or equal to relation is a partial order, but it is much more than that, because if we pick up any two elements, let us say a and b belonging to Z, not necessarily distinct, then we know that either a is less than or equal to b or b is less than or equal to a, or of course both. But in case both are true, then we know that a is equal to b. But what is important here is that given any two elements in Z, I can compare them. So, it gives a kind of ordering which is of course a partial order, but it is a special case of partial order which is called a total order. And the fact that given any two elements, either the first one is less than or equal to the second, or the second one is less than or equal to the first, is told in language as they can be compared. So, that means that any two elements in the set Z can be compared, and if that happens, then we call that a total order. And the set Z along with the partial order less than or equal to, which is a total order, will be called a totally ordered set. Now, we move on to a partial order which is not a total order. This is important because otherwise we do not have to study much, because then we will say that okay, all partial orders are total orders, but it is not so. But to establish that, we need an example. Now, we start with an element we start with a set containing two elements. Let us call that set S. then we construct all the subsets of this set S, and we denote it by P of S, which is first the empty set, then the set containing 1, then the set containing 2, and then the set containing 1 2. Now, the relation that we choose is the subset equal relation, that is conveniently denoted by the well known symbol of subset equality. So, if I am saying that A B belongs to P S and A is a subset of B, then that means that all the elements of A are in the elements of B. In other words, X belonging to A implies X belonging to B. All right, but this is essentially the well known definition of subset of another set, and here of course, I do not exclude the possibility that A is equal to B. Now, this relation is also a partial order. The reason is that if we take any subset A belonging to the set of all subsets of S, then A is a subset of A. Then if we consider two elements of the set P S and suppose A is a subset of B and B is a subset of A, then we will have A equal to B. So, the relation is antisymmetric, and if we have 3 elements A B C inside P S and A is a subset of B and B is a subset of C, this will imply A is a subset of C. Therefore, we have transitivity. So, I write here this is reflexive, this is antisymmetry, and the last one is transitive. Therefore, we can say that the power set of S with respect to the relation subset equal is a partially ordered set. In short, we write a partially ordered set as a poset. So, we will be sometimes writing as posets. Now, we would like to investigate whether this partially ordered set is a totally ordered set or not. For that, we consider two elements, the set 1 and the set 2, both belonging to the power set of S. Now, we see that 1 is not a subset of the set containing only 2 and the set containing only 2 is not a subset of the set containing only 1. Therefore, I have been able to produce from this very small set P S, which contains only 4 elements. I have been able to produce 2 elements, namely the set containing only 1 and the set containing only 2, which are not comparable. But I have checked that the properties of the partially ordered set, that is reflexivity, antisymmetry and transitivity, all hold for this set with respect to the partial order. Therefore, it is a partially ordered set which is not totally ordered. Now, we will move on to more examples on partially ordered set. We will take up a slightly bigger example than what we have done just now with the power set of 1 2. Our example will be the power set of the set containing 3 elements 1 2 3. Now, we can write the power set explicitly as this. It is phi, then set containing 1, set containing 2, set containing 3, then we have set containing 1 2, set containing 1 3, the set containing 2 3, and finally, the set containing 1 2 and 3. This is the power set, and just like before, we can consider the subset equal relation, and we can see that P S with the subset equal partial relation is a partially ordered set, or in short a poset. So, of course, we can again ask why it is so. We can finish off this whole chain of examples by a single proof, by taking any set and the corresponding P S, and show that P S with subset equal is a partially ordered set. I will give quickly an outline of that proof, which is pretty straightforward. So, I have now a set, essentially let us call it T. So, it is any set, and I am considering the set of all subsets of T, which is P of T. Now, we only have to consider the subset equal relation, and suppose A, B, C are subsets of T and therefore elements of P T. From very basic set theory, we know that reflexivity holds, that is A is a subset of A for all A belonging to P T, including the empty set. Then antisymmetry that is, if A is a subset of B and B is a subset of A, this will imply A equal to B, and finally transitivity that is A subset of B and B subset of C will force A to be a subset of C. These are very basic properties of set inclusion and equality. Therefore, we do not have to really worry much about these things. So, we have proved essentially once for all that P s with respect to subset equal is a partial order. Now, we will talk about representation of a partially ordered set. We go back to about 100 years to around the towards the end of the 19th century. So, we will so there was one mathematician, Helmut Hasse, from 1898 to 1979, who used certain diagrams to represent partial orders. These diagrams are referred to as Hasse diagram, following the name of Helmut Hasse, but historically there is another person who used Hasse diagram before Helmut Hasse, and that is Henry Gustav Vogt. In about 1895, it is recorded that Vogt was using diagrams which were essentially the same as Hasse diagram, but since Hasse have been using it extensively, the name of the diagram is Hasse diagram. Now, we will take up the partial order that we have already seen. Let us see that one, that is the set containing 1 2 and the power set of the set containing 1 2, which is phi 1 2 and 1 2. Now, suppose we try to draw the digraph corresponding to this partial order, then we will write 4 points on the plane. So, we write phi, which is the MC set, then 1, which is the singleton containing 1, 2, this is the singleton containing 2, and the set 1 2. Now, we will start joining these points or nodes by directed edges. So, first of all, if I start from phi, I know that phi is related to itself. So, I draw a self loop, and I also know that phi is related to 1. So, I draw an arrow like this. Then I know that phi is related to 2. Therefore, I draw a arrow like this, and finally, I draw an arrow from phi to 1 2, put a arrowhead in the proper direction. Then I start from 1. I know that 1 is related to itself. So, I draw like this, and I know that 1 is related to 1 2. So, I draw an arrow like this. I come to 2 now, 2 is related to itself. So, I draw a self loop over here, and 2 is related to 1 2. So, I draw a arrowhead with arrow, and finally, 1 2 is related to itself. So, I draw like this. What I have here is a digraph corresponding to P s with respect to the subset equality partial order. So, I can write like this, it is P s semicolon the partial order written inside a bracket. What we note here that there are many edges that we could have removed. First of all, when we are dealing with partial orders, then we know that each node will have a self loop. So, there is no point drawing a self loop at each node if we are certain that we are discussing partial orders. Therefore, we can do with the self nodes. So, we can remove the self nodes, and so if we do that, let us in rough see what will happen here. So, it will just get something like this. Okay, so, we will put 4 nodes over here, arrows are still there, and then I will put phi over here, 1 over here, 2 over here, and 1 2 over here. Once I do that, and no, here I will have something more, I will have this edge. Once I have this, I note that this edge is also redundant. The question is why? Because we know that we are dealing with partial orders, and since we are dealing with partial orders, therefore, it is transitive. Therefore, if for example, there is one node, let us say A, which is related to another node B, which is again related to another node C, then of course, you will have an edge from A to C. For example, if then C is related to another node D, then we will have an edge from B to D and from A to D. All right. Now, what I say is that we really do not have to consider these edges that we derive later. We can say that it is transitive. So, there is an edge between 2 nodes if there is a path from the first node to the other. So, we can remove those edges. Therefore, ultimately we will have a very simple diagram removing this, but wait a moment, we can do something more. We can take the elements in the partially ordered set in some kind of hierarchy and draw them in a kind of layer by layer going bottom up, so that the arrowhead is also understood. In this case, for example, if you consider phi, you will see that it is kind of the lowest node or lowest point in the partial order set, because no point gets connected to it from below. Therefore, I will start from here and I will now write 2 points 1 and 2 on a layer above, noting that there is no point in between phi and 1, because we do not have any element such that phi is related to that element and that element is related to 1. So, therefore, I write 1 and 2 is an element like that, and of course, 1 2 is not an element like that. Therefore, I write 1 and 2 and then connect them, and I deliberately do not draw arrowheads. It is understood that the arrow is moving upward, and then after that I have 1 2, I will draw in this way and finish off with the diagram. So, I have a diagram like this, which I call a Hasse diagram. Which is much more simplified than the digraph corresponding to a relation. Of course, we can do it only in case of a partial or partially ordered set, that is only in case the set is reflexive, the order relation is reflexive, antisymmetric and transitive. Now, we will take up the problem of drawing Hasse diagrams. So, we start with the Hasse diagram of S equal to 1 to 3 and the power set corresponding to that set. So, let us now look at this example. We have S 1 2 3, and we are considering the power set of the set 1 to 3 denoted by P s, and let us write explicitly all the elements. So, it is phi, then 1 2, then we have 3, then we have 1 2, then we have 1 3, then we have 2 3, and lastly we have 1 2 3. Just same as before, we see that the element phi is let me reword my sentence, no element in P s is related to phi. Therefore, we start with phi. We draw this is phi. Now, we will try to pick up elements such that phi is related to those elements, but there is no intermediate element in between, and the singleton sets will serve my purpose. So, I will write here the set 1, here I will write the set 2, and here I will write the set 3. Now, we see that I have a direct relation from phi to 2. So, this is a straight line, this is a straight line, and this is a straight line. Now, what I do is that I draw next layer of elements this is 1 2. So, 1 is of course related to 1 2. So, I will join 1 and 1 2, and 2 is of course related to 1 2. So, I will join 2 and 1 2. Then I will draw 1 3, 1 is related to 1 3, 3 is related to 1 3, and here I will write 2 3 and join them. So, I have got the other the next layer of elements, all right, and ultimately I have got a single element 1 2 3, and I can complete my diagram in this way. So, this is the Hasse diagram corresponding to the set P S with subset equal relation, where S equal to 1 to 3. So, we will end today's talk by another Hasse diagram. Now, let us look at that one. First, let us consider a partially ordered set, I call it I 6, which contains integers between 1 to 6. And the partial order that we define is divides, and we denote this partial order by a vertical line. So, we will write A divides B if and only if A divides B in the usual sense. So, strictly speaking, I can say that A divides B if and only if there exists C belonging to Z such that B equal to C times A. So, this is the standard definition of division that we are using. Now, on the set of all integers between 1 to 6, let us consider this relation. It is not difficult to see that it is also a partial order. The question is why? Because if I take up any element A inside I 6, then of course A divides A, and if I take up any two elements inside I 6 such that A divides B and B divides A, then from very basic property of division I can infer that A equal to B. And finally, for A comma B comma C, 3 elements in I 6, A divides B and B divides C automatically means A divides C. So, these are properties of division. Now, I would like to write down explicitly the partial order corresponding to this divides. So, see that I will have 1 1 and then I will have 1 2, then I will have 1 3 then I will have 1 4, then I will have 1 5 and 1 6. Then starting from 2 I have 2 2 and then 2 4 and 2 6. Starting from 3 I have only 3 3 and 3 6. Starting from 4 I have only 4 4 and then I have 5 5 and I have 6 6. This is the relation. Now, if I want to draw a Hasse diagram corresponding to this relation, I will keep 1 at the bottom because nothing divides 1, and then check out all the numbers, particularly the prime numbers. So, 1 1 1 I need not consider. So, I get 1 2, right. So, I will draw like this, and then let us consider 3 also. So, I have got 3, the 1 2, I have got 1 3 and then 1 4, but I am not going to draw 1 4 because 2 is related to 4. So, it will start from here and go upward to 4. This is 4, and I am not going to draw 1 6 because 3 is related to 6. So, I will start from 3 and go up to 6. This is 6 and see 2 is related to 6 also. So, I have got this. Then I have got 1 2 3 4 6. There is only one element that remains outside this set, that is 5. I draw 5 over here. So, this is a Hasse diagram. This is different from the ones we have seen before. Like this, there are other Hasse diagrams that one can draw, and that one has to try as exercise. So, we stop our discussions on partially ordered set and representation of partially ordered sets by using Hasse diagram here. Thank you.